Our next lesson is Vectors 2 on axis rotation. And in this lesson we're going to talk about Galilean transformations, and we'll talk about axis rotation and using that to solve vector problems. So, Galileo Galilei, the famous scientist, studied motion mostly, so he's most famous for, noticed that the physics of moving objects appear to change if you stretch, bend, or distort the coordinate system, but the physics doesn't change if you shift it. That's what's called technically translation. You reflect it or rotate the coordinate system. And to some extent this sort of makes sense. You could imagine, two people who are running a race that run exactly the same speed, and they're running the same distance at right angles to each other. If you were to distort the coordinate system so that the y-axis, so that one axis was squished, it would seem that one person should win the race before the other one does, even though they would be running at the same rate and the same technical distance. It would throw things off. And so things that distort, stretch, and bend coordinate systems are problems. Is that so in a Galilean sense, and we'll get to this a little bit briefly, but this deals with basically things that act like normal everyday objects. This doesn't apply to things that are really, really tiny, like on the order of atoms and things smaller than that, and it doesn't apply to things that are going really, really fast near the speed of light. But for most everyday things, this is true. So if you stretch, bend, or distort the coordinate system, it throws off the physics. Physics does not act the same in a stretching or bending coordinate system or distorted coordinate system, but it doesn't make a difference if you shift the coordinate system, like you move it around, basically in the same way. These two people are running, and you're standing, right where they start, and you time them. That you'll get the same result for both of them. It doesn't make a difference whether you're starting where they started, or started where either one of them stopped, or standing on a hill nearby. They'll still both get to the end of the race at the same speed. It doesn't change the physics if you move around where your coordinate system is, if you just shift it or translate it. It doesn't make a difference whether you reflect it. If you take that and mirror it, if you were to watch the thing in a mirror, watch the race in a mirror, where everyone's running in an opposite direction they would have before, does it change the result of the race? No. Mirroring or reflecting your coordinate system makes no difference. Same thing is true with rotation. If you watch it from one side of the track and then move around, and so you're looking at it from a different angle, so that before one person is running sort of at an angle of 45 and the other person's running an angle of 45, and then you shift so that now one person's running at 60 and the other person's running at 30 degrees, it doesn't change the result of your system. So as a result, if we start off with this nice set of vectors here that we're adding up, is that this is what we start with. If we were to shift this around, we'd be okay. We're good. If we were to simply rotate this guy, we'd be okay. We still have the same physics going on. We could take the original guy and we can mirror him horizontally, and so he's exactly backwards. We still get the same physics. We add these vectors up, we'll get the same vector. It really doesn't make it may be pointing a different direction, but in reality it's really the same vector. But on the other hand, if we were to take that and we were to squish it, we were to distort the coordinate system in the x direction, then we get to a system that doesn't work. Is that you can't manage to bend, distort, to stretch any of your coordinate system and have the physics stay the same. And so therefore, whenever you're drawing something out, when you're doing a diagram, you can do any of the three exceptions: translation, reflection, or rotation. These are called the Galilean transformations, but you can't stretch, bend, or distort your coordinate system whenever you're taking data and watching sort of motion, and so we're looking at vectors. So these three exceptions, these Galilean transformations, you may do any of these three things to your coordinate system without changing the physics, and so that means it's okay to do those when you're sketching things out, when you're actually solving a problem. So just as I mentioned before, is this doesn't apply to things very, very fast. It turns out the Galilean transformations fall apart when you start getting near the speed of light. This is one of the things that Einstein discovered. That's part of his theory of relativity. Then you get to a fair amount. It adds a little more complexity to it, and you actually have to do what's called a Lorentz transformation in order to get it to set up. But we're not going to get to those for this section. So onward we go. Let's look at how this might be useful. Specifically, it's axis rotation. One of those three. Translation maybe is a little bit useful. I mean, that's really what you do whenever you move vectors around to add them head to tail. All you're really doing there is you're doing a translation of your vectors. It didn't change them. reflection really doesn't make a difference, but axis rotation, this one ends up being really useful. Said we can rotate our coordinate system, and we can sometimes use that to find resultants we otherwise couldn't. Mostly by taking resultants that we basically aim them along an axis. And by aiming them along an axis, we basically we make it such that the overall change in either x or y, whichever axis we put it on, if we rotate it so a vector sits on the x-axis, we know the other two vectors have to have a total y value then of 0 when we add them up. And that gets rid of one of our variables. And so it lets us solve things we couldn't otherwise. So the only thing you have to watch out for is this second part that's going on here. Once a system of vectors has been solved, if the original question asked for a direction, the system must be rotated back to the original configuration if you rotated the axis in the first place. And so, if you started off with, I've got this vector right here and this vector right here, and you said, I'm going to rotate this so that now I have this vector right here, that's my first vector, and the other one points back this way. If I did that and I used that to find that, there's my component right there, to actually, if I wanted to find that angle in that component, I would have to then rotate it back again to the original system so that I had my, so I had that original one that I set up so that I had that there. And so, which isn't too difficult, because if I know that I rotated the first one over by, 60 degrees, and I got for this vector right here that say that it's at an angle of 135 degrees, then I simply take 135 minus 60, and so I know that it's it's 75 degrees in that case. Must be the heading. So it's really not that difficult to do, but you must remember to, if you rotate the coordinate system, to when you're done, rotate it back to the original configuration. Okay, so when you're rotating your coordinate system, you can choose any axis rotation that you wish to, but most possible rotations are stupid, honestly. You rotate it by 2 degrees for no good reason, it isn't going to help you any. It is generally best to rotate the coordinate system so that one of the vectors that you know the direction for, but not the magnitude for, is along either the x-axis or the y-axis. Doesn't make a difference whether it's x or y-axis, or positive x or negative x, it doesn't make a difference that way. But you do want to take a vector where you know the direction but not the magnitude, and rotate that so it lies along one of the cardinal directions. And so that would be the advice I would give there going forward on that. So, that being said, let's work out an example. A jet with an airspeed of 205 meters per second pointed at 30 degrees is knocked off course by a 33 meter per second wind at a heading to a heading of 45 degrees. So what's the total speed of the jet? And so in this case, we don't know the direction of the wind. We do know that they end up going 45. So let's see if we can set this up here. So the jet is pointed at 30 degrees. And so let's see if we can sketch this out. So we have this jet here heading up this direction. We know that the angle that it takes in here is going to be 30 degrees right in there. We've got that. We know that the magnitude of this guy right here is going to be 205 right there. We know that there is a 33 meter per second wind. We don't know what direction it's going. We do know that whenever it's done, the jet now has a resultant at 45 degrees. So what's a 45 right down there? So 45 degrees right there. So the wind, has to be that, and this, we really don't know which direction that is. I mean, I sort of arbitrarily drew it that way. We know it's 33, but that's about it. We really don't know too much else about this. We don't know the actual angle that 33, that wind vector is. It could be like I have it. It could be pretty much pointing almost straight down. We really don't have any information as far as that. That 33 could be pointing most anywhere. We sketch it out in one place because we have to sketch it out some way. But otherwise, we have two lengths. We have an angle in between one of them, but we really don't have enough information to be able to solve this the traditional way. Or there may be another way to do it using law of sines, law of cosines. But for right now, let's worry about how we do it this way. So the trick is on an axis rotation is you want to rotate it so that one of the vectors that you don't know the magnitude for, but you do know the angle for, is pointing along an axis. And in this case, that'll be the resultant, the one that's at 45 degrees. And so we are going to take this thing, we're going to take this whole system, and we are going to rotate it, in this case, in the clockwise direction by 45 degrees. And if we rotate it at 45 degrees, then now this 205 vector is not going to be at 30 degrees. It's going to be at 30 plus 45, and so it would now be at 75 degrees. And so resketching this, we've got this vector right here, which is now at 75 degrees, and still has a magnitude of 205. We know that the 33 vector is going to, I'll just sketch out the axis a little bit farther. The 33 vector is going to come down here, that we know that's the wind. But we know that when we add these up, we now get our resultant vector, which now points directly along the x-axis. Now, let's see how this is useful. So let's break these guys into components. So let's take the 205. The 205 comes up like this. We have one component this way, one component this way. So for the 205, here's what we can say. We can take that right there and we can say, okay, that the x component is going to be the opposite. So we have 205 opposite over hypotenuse is going to be sine. So 205 times sine of 75. Okay, for x. And so if you get out your calculator on that, we find we have 205 sine of 75, which gives us 198.01 is our x hat for that one. For our y hat, it would be, in this case right here, 205 cosine 75. So I don't see any reason to write that down. I think you guys get the idea. So 53.06 y hat. Let's see, both are positive in this case. That's a y hat. But let's take a look at the 33 now. The 33, to break it into components, has a downward component like this, and it has an over component like that. But look very carefully. Because of the fact we redirected that total resultant so it goes along the x-axis, that means that we know that the y component of the 33 in there, this little section right in there, has to be the same length as the y component of the 205. So if we set up our 33 one here, if we sort of sketch this again, here's our 33 like this. We broke it up into two components, this one and this one. We know that that y component has to be the same thing as the other one, which is 53.06. Now, it is going to be negative because of the fact it's downward, but that lets us solve this because we know the hypotenuse is 33. If we know the hypotenuse is 33 and we know one side is 53.06, this is a right triangle. We can find the other one. All we have to do is, we've got a slight problem here. Let's take a look at what we've got. All right, well, I made a slight mistake in here. Obviously, it's not possible to have a triangle that has one side that's 53 and another side that's 33. And so to make this work a little bit better, what I'm going to do is I'm going to change this, instead of being 33, I'm going to make it into 83. And so make that an 8. Shouldn't change anything we've done so far. Make that an 8 down there, 83 and 83, like that. Now we should be able to work this out. So we've got 83 here, so just use Pythagorean theorem. So 83 squared minus 53.06 squared, and then we take the square root of that, is 63.8 is what we get for that section right down there. So this right here is 63.83. So that means that we now basically know the two x components here. We know the x component of the first vector with the plane's airspeed is 198.01. We know that the component of the wind in the x direction, our rotated x direction, is 63.83. And so if we were to take those two and we were to add them up, that would give us a number that's too large here, if you notice, and you'll see this here. So I take 198.01 plus so 63.83. And what do you notice? We get 261.84. The problem with that is our total speed's 205. So actually it's not a problem here, because if we have our total speed is 205, then the wind is going to point us off, and so it's going to knock us a little bit faster here. And so as a result, we get a total for this length of 261.84, and this unit's going to be meters per second right there. And so in this case, since that component that's right in there, sort of our x component here, plus this x component here will give us that total length right there, then this must be the total speed of the jet. Now, if we had been asked what's the velocity of the jet, we'd also have to get its angle. And so to do that, we'd have to get the angle, and then we'd have to rotate it back to the original coordinate system. And so keep that in mind. Final answers, figures, we have 3 sig figs here. We have 2 for the 83 that's right here. So that means that for all of our 205 stuff should have had 3. So these would have been down to the basically to the ones place on each one of those. So this one should be down to the ones place on our 198. This one over here, the 83, had 2 sig figs. Should have been routed to the ones place based on that, because we had to do Pythagorean theorem. It was a little addition there. So our final answer should be routed to the ones place. So it's 262 meters per second would be our final answer.